Hey you guys, so this is problem number 55 from section 8 from chapter 4, and it's a section on node voltage versus mesh method. So first let's talk about, describe the circuit, and then we'll read the problem. So we have two 125 volt independent voltage sources and a connection of resistors. This is 0.3, 0.5, 0.3, this is 9.2, 19.2, and 11.6 ohms resistance. So the problem says this circuit is a DC version of a typical 3-wire distribution circuit system. These resistors right here, they represent the resistances of 3 conductors that connect the 3 loads, and these are the loads 19.2, 19.2, and 11.6. Those are the loads that are connected to the 125 250 volt voltage supply. These resistors here, 1 and 2, they represent loads connected to the 125 volt circuits, and this one connects to the 250. Question A. So which circuit analysis will you use and why? In my opinion, this one is very clearly, well, first of all, let's see how many unknowns and how many unknowns we have. So with the mesh, we have clearly 3 meshes, 1, 2, 3. And in just doing a preliminary look at what kind of equation it's going to look, it looks pretty straightforward. So the mesh has 3 equations and 3 unknowns, and they look to be pretty straightforward equations. Let's check out the node voltage. So we got one node here, a node here, a node here, and one node, which we're going to take to be the ground node. That means we have 3 unknowns. So both mesh and node have 3 equations and 3 unknowns. However, mesh is going to be far easier because of the equations that you have to write are very straightforward. And the node voltage is going to be hard because of this node right here. Because from here to here, how do you write what is your voltage here and what is your voltage here? So the node voltage method is the more tricky one, in my opinion. Answer to part A is that they both have the same number of equations, same number of unknowns. However, the mesh method is much easier because the equations are more straightforward. Now, in part B, we need to calculate V1, V2, and V3. That's the voltage drop here, here, and here. And the method we're going to use is, we're going to do the harder technique, because I already know that you can do it via the mesh method. So I wanted to show you how we would handle this tricky guy right here. So we're going to do it by the harder method. So that you have an additional skill, so you know how to handle it when you have a tricky node. So, having said that, let's go ahead and find the V1, V2, and V3 using the node voltage method. So, I'm going to call them different names and come back to V1, V2, V3 at the very end. This node I'm going to call VA. That's some node, that's some voltage drop that I have no idea what it is. This is my second node. I have no idea what it is. We're going to call that VB. This is my third node. This is VC. And this is my fourth node I take to be the ground. Okay. So let's start writing our node equation. We're going to start at the hardest node of all. Node at VA. So remember KCL, node voltage takes advantage of KCL. We're looking at the sum of the currents leaving the node must equal 0. So let's take a look at this current here. So remember, current is voltage over resistance. So it's going to be the difference of the voltages divided by the resistance. The resistance is the easy part. The voltage is the hard part. So what is this voltage here minus this voltage here? This voltage here starts with VA. That much is clear. But how do we handle this right here? Well, there's a current that's leaving the node, right? And as it leaves the node, it goes through a 125 volt independent voltage source, And as it goes through the 125 voltage source, it goes from a negative potential to a positive potential. Just like your checking account, when you go from negative to positive, you've gone up. So, as this current goes through, it's going through a voltage rise. And therefore, that tells me that this total voltage here is going to be VA plus 125. So VA plus 125 is on the one side of the voltage minus VB divided by 0.3. That's current number 1. Current number 2 is extremely straightforward, thankfully. So the second current is VA minus VC over 0.5. The third current leaving here starts at VA. And it's going to be minus 0 because our reference node is the ground. So as this current is leaving, it's going through this independent 125 volt independent voltage source. And as it goes through, it's going through from plus to minus. So from plus to minus means we went through a voltage drop. So that means that this 125 must be a minus. So the final current is going to be VA minus 125 minus 0. We're not going to put the minus 0 there, but that's the other side of the node is the ground node, and that's going to be over 0.3. All that must equal 0. Okay, just wanted to make sure you everything is visible. So that is going to be node voltage at VA. So node voltage at VB, this is the straightforward, kind of straightforward, I guess. So the first one is going to be VB minus, and again, we're looking at this current leaving, right? KCL is about the sum of the currents leaving being equal to 0, and as it goes through here, it's going to go through from plus to minus. That is a voltage drop. We went from positive potential to negative potential, so that's going to be minus the 125 this time. And also minus the VA. All that is going to be over 0.3. Next term is going to be VB minus VC. That's going to be over 9.2. And the third current is going to go straight to the ground node, so VB over 11.6. All that must equal 0. The final node is the VC, node voltage at VC. This is going to be our most straightforward node. So first branch current, let's take VC minus VB over 9.2 plus VC minus VA over 0.5 plus VC over 19.2. That's equal to 0. So anyways, that is how you set up the equation with the tricky one. Originally I solved this problem using mesh, and it was super easy. And I decided that it's harder to find problems solved the tricky way. Everybody will want to solve it the easy way. But even though on an exam I don't recommend you do it this way, I recommend that you know how to do it. So now we're going to set up the matrix for those 3 equations. So we got 3 variables, VA, VB, and VC, and constants. So we're going to inventory our coefficients. So for VA, we have 1 over 0.3. And then we have another 1 over 0.5, plus 1 over 0.5, and then 1 over 0.3. Those are the coefficients for VA. For VB, we have a negative 1 over 0.3. And for, do we have any VB anywhere else? Nope. And for VC, we have -1 over 0.5. And then for constants, we have a plus 125 over 3. And then over here, we have a minus 125 over 0.3. So they will cancel each other out. And on this side, we have 0 constants. Second equation we have is for VA, we have one term and we have a -1 over 0.3. So for VB, we have 1 over 0.3, 1 over 9.2, and 1 over 11.6. 1 over 0.3 plus 1 over 9.2 plus 1 over 11.6. And for VC, we have a -1 over 9.2. And for constants, we have this -125 over 0.3, which will go on the other side as a positive. Positive 125 over 0.3. Okay. Now the final equation we have for our VA, we have -1 over 0.5. For VB, we have -1 over 9.2. And for VC, we have 1 over 9.2 plus 1 over 0.5 plus 1 over 19.2 and 0 for constants. That's our matrix. So let's go ahead and enter the information into our matrix and find out what VA, VB, and VC are. But first, let me make sure the entire screen is available. Okay, so it looks like part of it is chopped off. Sorry, you guys. I know I should get one of those things that write onto it, but I just haven't got around to it. Okay, so we have 3 equations and 3 unknowns. So 1 divided by 0.3 plus 1 divided by 0.5 plus 1 divided by 0.3. -1 divided by 0.3, -1 divided by 0.5, and 0. -1 divided by 0.3, 1 divided by 0.3, plus 1 divided by 9.2, plus 1 divided by 11.6. And then -1 divided by 9.2. 125 divided by 0.3. -1 divided by 0.5. -1 divided by 9.2, 1 divided by 9.2, plus 1 divided by 0.5, plus 1 divided by 19.2, and 0. Solve. And I'm going to check this against what I got the first time. And it is the same. Okay, so this is what you should have got. Okay, so what you should have found out is your answer should have been VA is 117.11, VB is 232.44, and VC is 120.09. So what were we originally looking for? We were looking for V1 plus V1, which is the voltage drop across the 9.2 ohm resistor, and V2, which is the voltage drop across the 19.2 ohm resistor, and V3, which is the voltage drop across the 11.6 ohm resistor. Well, V3 is really VB, so this is V3. And VC is really VC is really V2, so that's going to be V2 right there. And VA, V1 is going to be VB minus VC. So that's going to be, where is V2? Oh, VB, which is 232.44, minus VC, which is 120.09. So we got 232.44 minus 120.09. So this is going to be, V1 is going to be 112.35 volts. So that's the answer to part A. V1 is 112.35, V2 is 120.09, and the third V3 is 232.44. All right, so that's part B. Part C says, calculate the power delivered to R1, R2, and R3. Well, power is just V squared over R. So power delivered to P1 is going to be V1 squared over 9.2. I'm going to let you do the math and tell you that that should be 1372.01 watts. P2 is going to be V2 squared over 19.2. Do the math and it should come to 751.13. P3 is going to be V3 squared over 11.6. That will give you 46.57.62. Okay? So the power delivered is going to be the sum of those three. So power delivered, or excuse me, power delivered. So power delivered, the power delivered is going to be, add those three together and you should come up with, I actually didn't do it, so 1372.01 plus 751.13 plus 4657.62, that gives me 6780.76. So that's the total power delivered to the circuit. Part D asks, what percentage of the total power developed by the sources is delivered to the loads? Well, power developed, we need to figure out how much power is developed by the two voltage sources. So let's take the case of this one right here. So P is equal to VI. The V is easy, right? The V is just 125. What's the I though? Well, let's consider the current going through when we did KCL here. When we did KCL here, when we did the node voltage at V1, we had to find that branch current. So let's find that branch current right now. The branch current leaving the node going through, that is going to be on this side. So we're looking for I is equal to V over R. So in this case, the V is going to be the VA, which we found out to be, what did we say VA was? We said VA was 117. So that's going to be we're starting at 117.11. We're going through, the positive current is going through a voltage rise, so that's going to be plus 125. And then minus VB, which is 232.44, and then the resistance is 0.3. That's the current that's going to go through that. So we got 117.11 plus 125 minus 232.44. Divide that by 0.3. And so that's going to be 32.23 amps that's going through that voltage source. Now the current enters the negative terminal, so power is going to be there's your current, VI, right? But what's the V? The current is going through, start a voltage rise, so it enters the negative terminal. So that's going to be negative 125 volts. So 32.23 times negative 125 gives me negative 4029.17. So that's the power that is generated by that voltage source. Now we're going to do the same thing for that voltage source. So consider the current going through here. It's going through the ground node. So it's going to be VA, which we said was 1, so I2, the second current, that's going to be starting at VA, which is 117.11. It's going to go through a voltage drop, right? From minus to plus is a drop. So that's going to be minus 125 volts, and that's going to be over 0.3. So we got 117.11 minus 125. Divide that by 0.3. And that gives me negative 26.3 amps. That current is entering the negative terminal, or the positive terminal. So that voltage is going to be a positive. So power of the second source is going to be negative 26.3 amps. And the sign of the voltage will be positive because it's entering the positive terminal. So times plus 125. So that's going to give me times 125 is going to be negative 3287.5. Okay, so now the total power is going to be the sum of those two. So power total. So power developed, PDEV, is going to be the negative 40.29 plus the negative 3287, and that's going to be negative 7316.67. So percentage power delivered, percentage power dev is going to be 6780.76. We're looking for a ratio, so the sign doesn't matter. 7316.67. So we're going to go 6780.76, divide that by 7716.67, and okay, so I have a mistake somewhere. Let me figure out where 7316.67 is correct. So then 1372.01 plus 751.13 plus 4657.62. Oh, typo. So from 73 I put 77 for no good reason. That should be 73. Okay, so 6780.76, divide that by 7316.67. This is more like it. So that's going to give me 92.68% efficiency. Okay. So the answer to part D is 92.68%. So now part E. Part E says, part E, one second. Part E says, now we're going to open that 0.5 circuit and asks what happens when we open that. So it says the RB branch represents a neutral conductor in the distribution circuit. What adverse effect occurs if the neutral is open? And so they want us to, the hint that they've given us is recalculate V1 and V2, and note that appliances or loads designed for use in this circuit would have a nominal voltage rating of 125 volts. So something about the 125 volts is going to be key. And bad things will happen apparently if the neutral is open. Clearly that must be true, or else the design, they wouldn't just randomly put in a resistor and incur more cost, unless bad things did happen that they had to prevent. Now, since we already did the node voltage, clearly the node voltage would be complicated in this case, and we're not going to do it the more complicated way. This time we're going to take the path of least resistance, electrical circuits humor there, and we're going to do the mesh method because clearly it's a much easier method. So we're going to go IA and IB. Okay? Now these are series connected, so we could, if we wanted to, we could combine them. But since they're asking for the voltage drop here and here, there's no sense in combining them. So now, finally, we're going to take the easy way. And these we can combine to 250. And in fact, I'm going to combine them into 250 because there's no advantage in not doing that. So let's start the mesh at IA. Mesh at IA is going to be minus 250 plus 0.3 IA. Let's go ahead and combine that. We'll break it out after we figure out what the voltage drop is. Okay. Alright, so 9.2 plus 19.2, that's going to give me 28.4. So it's going to be plus 28.4 times IA minus IB, and then plus, I'm going to combine these two and make this 0.6. And that's going to equal 0. Mesh at IB, that's going to be 28.4 times IB minus IA plus 11.6 IB must equal 0. Alright, so we have a very simple matrix. We got IA, IB, and constants. IA, IB, and constants. Equation 1, the first term is negative 250. It's going to come on the other side as positive 250. IA, we have a 0.6 plus 28.4. And then for IB, we have negative 28.4. Second equation, we have 28.4 for IB plus 11.6. And then for IA, we have negative 28.4 and 0 for constants. So let's find out what IA and IB are. So we have two equations and two unknowns. It's going to be 0.6 plus 28.4, negative 28.4, and 250, negative 28.4, and then 28.4 plus 11.6 and 0, solve. Okay. I clearly made a mistake somewhere, so that's what happens when you take shortcuts. So let's see, where did I make my mistake? So for this one, IA should be. So I have IA of 0.6 plus 28.4. And then, so let's go ahead and go through 19, 9.2, 9.6, so 0.6 IA. And then 28.4 times IA minus IB. That's correct. And then 28.4 IB minus 28.4, 11.6. Let's try this again. Maybe I just typed it wrong. Okay, so 0.6 plus 28.4. Negative 28.4, 250. Negative 28.4, oops, negative 28.4. 28.4 plus 11.6 and 0. Okay, so apparently this matrix is right, but I had some fat fingers in there that gave me a really weird answer. But the equations are correct, just a fat finger. Right, so let me double check again. Yes, that's what I got the first time. So what we found out is that IA is 28.29 amps. IB is 20.09 amps. So they want us to look at V1 and V2. V1, this is V1, and this is V2. So originally, let's compare. The original V1 and V2 with the neutral in place. So the original V1 and V2 with the neutral in place gave us was V1 was 112.35 and V2 was 120.09. Now, when we remove the neutral, clearly that will change the situation. So V1 is going to be, well, it's going to be I minus R, so the R is 9.2, and the I is going to be I1. So 28.29 minus 20.09. That gives me, okay, so 28.29 minus 20.09, that's going to be 7.39 times 9.2, so that is 67.99. I don't feel like that's what I got the first time, so let me just double check. 28 minus 20.09. So 28. Oops. I'm full of typos today. This isn't 739. So 28.29 minus 20.09. That is 8.2. So times 9.2. This is 75.44. And that's what I got before. Okay, so then V2 is going to be 19.2 times 8.2. So 19.2 times 8.2. That's going to be 157.44. So, and that's what I got before. So now, let's go back and revisit. So without the neutral, V1 drops from 112.35 to 75.44. And that's not problematic. It's V2 that's going to be problematic. V2 is going to be 120.09 and spikes all the way up to 157.44, which is well over the 125 volts. So since most appliances, the hint that we have here is that bear in mind, note that appliances or loads designed for use in the circuit would have a nominal voltage rating of 125. So clearly for V2 to spike up to 157.44 is hazardous. So that's why they put in the neutral, to divide the voltage and cut it down, to bring it down to 120, which is in line with how appliances are designed. The other way they could do that is obviously to redesign appliances to be at 157, but that's not how the world works, so we have to cut the voltage down with a neutral. Okay, you guys, that is the end of this problem. Be sure to like the Facebook and share the video, and all right, I hope I did more help than harm.